Welcome to week 3. And this week we're going to introduce higher order differential equations. So equations with more than first derivatives. We're talking second and third and higher order derivatives. And we're going to look at some of the general patterns we can see with those kinds of differential equations. And we're going to try to start that off with looking at an application where these kinds of equations arise naturally. We're going to consider this spring system, and we're going to return to this example several times through the course, so it's an important idea, important example to keep in mind. What we're going to imagine is that we have a coiled spring, and we have a mass attached to it. And what this mass is going to do, of course, is oscillate back and forth. So when we see something about oscillations, we might expect to see any kind of time we see oscillations, we might expect to see mathematics very similar to the math we're going to see for this system here. And that's a nice model because if we look at the parts, there's a mass and there's a spring, and that's about all there is to it. So it's nice and simple and hopefully leads to some natural intuitions about what's going to happen when we start this spring system going under various conditions. It's important to recognize right off the bat, though, that this simple system has analogs in a variety of different structures. One of the most obvious places you'd find this is in a car. You see a spring system in a car at the suspension points for the drivetrain, when we actually have the body of the car being supported by springs to separate it from the road and make the ride a bit smoother. And if you look at different cars or ride in different cars, you can feel the difference about different designs, different masses, and different springs, and the effect that has on what it feels like to be in the car. On a much smaller scale, we can think about sound coming in and having a piece of drywall be like a mass that's going to oscillate back and forth when there's an external force being applied. And so if we tap on a wall of sheetrock, it'll oscillate. And if you look at how sound studios are designed, this is an important effect to take into consideration, how incoming sound waves affect flat surfaces. And it has the same, slightly more complicated math, but it can be idealized as a simple mass with a certain springiness to it that would oscillate under certain conditions. That's a very small scale example. If you want to look at very large scale examples of where we might see this kind of spring mass system, this particular mass you see here weighs 730 tons. It's a monstrous ball, larger than a person, about 2 people tall. And it exists at the top of the Taipei 101 building, so one of the tallest structures in the world today. And it turns out that the mathematics behind a large pendulum like this, which is essentially a ball at the end of a chain, which can swing back and forth, it's very similar to the mass attached to a spring, which can move side to side. The mathematical formulations you get are almost identical if the swing is small. And so we can look at or model this monstrous huge ball here, which is sitting at the top of a very, very tall tower, swinging back and forth. We can model it as if it was a mass on a spring and then predict what's going to happen. And that's what we're going to be interested in, is understanding how these different scenarios with different masses and different spring constants are going to be what they're going to have in common mathematically, and what we can learn from that mathematical model about how they would behave under different conditions.